In Module 2, we're going to see how can we formulate structural reliability problems. So how can we formulate reliability problems? There are two cases. First, we're going to see the special case where we're going to directly model RNS, their resistance and solicitation, using random variable themselves. Then we're going to see that this simple case as limitation, and we're going to expand this to the general case where we're going to have limit state function. So we're going to have random variables that are involved in defining both the solicitation and resistance. So instead of directly modeling R and S as random variable, we might model a wide range of random variable that are involved in resistance and solicitation modeling. And this is really what's going to be behind the general case for structural reliability problems. So in module 2, we're going to see the case of resistance and solicitation modeling, the simplest case you can model a reliability problem with. Then we're going to see what we left on last module. How do we choose the probability density function for a given problem? Why does it matter? And then we're going to expand onto the general case where we're going to define what we're going to see is FEL for limit state function. So a function that defines the boundary between the survival and the failure domain. And we're here in module 2. This is the first module where we're looking at structural reliability. And in this case specifically, how do we define, how do we formulate a reliability problem? So this is one of the key modules from the entire class. So first subsection, special case, how to model a structural reliability problem by directly representing the resistance and solicitation as random variable themselves. So we're going to look first at the apply example. Then we're going to look at three specific methods. So first, if we define conditional density distribution function and use them to compute our probability of failure, then we're going to look at a safety margin concept, then a safety factor concept. And you're going to see from these, we're going to define, we're going to use throughout the class, and what is used throughout the concept of reliability theory is beta or reliability index. So from these methods we're going to see here, we're going to see transpiring that beta, that reliability index that is used everywhere. And finally, we're going to see how modeling rare events requires specific thinking about the choice of probability distribution to model all the quantities involved in our problem. So first, let's start with the special case where we're going to explicitly define the resistance and solicitation as random variables. So my first random variable R model the resistance. The second one, S, is going to model the solicitation. So the force applied on my bar, if you want. I'm going to have two possible states because in reliability, remember, only two states, either failure or survival. So if my resistance is lesser or equal than my solicitation, I'm going to be in my failure state. If we have the opposite, the resistance is greater than S, we're going to have survival. And note here that the case where the resistance is equal to solicitation, we're going to define the context of reliability as being to the failure domain. So the probability of failure can be defined as PF. So the probability that my resistance is less or equal than S, my failure event here. And my reliability, which is going to be the complement of the probability of failure, is going to be 1 minus PF. So in terms of reliability, we're always going to quantify PF, not its complement, because this is going to give a number that is easier to work with. It's going to be, say, 10 to the minus 4, which is going to be easier to deal with than 0.9999. Okay, that's why even if we're interested in the reliability of our structure, we're computing and we're carrying on the failure probability. Okay, so let's look at a first example. We have R and S, which are both going to be modeled as log normal random variable. So S is my solicitation, the tensile force applied on my bar, R is the tensile resistance. So assume that the mean resistance is 20 kilonewton. My standard deviation for resistance is 5 kilonewton. For my solicitation, the expected value, the mean applied force is 20 kilonewton, the standard deviation is 5. And I assume that R is statistically independent from S. I can represent both on the same axis for both R and S, and the vertical axis is the probability density for both quantities. So remember what we saw initially in the introduction module, whereas in a lot of publications and a lot of civil engineering books, we represent that intersection as the probability of failure. But here, this is not the case at all. If we would compute the area in pink here, we would see that the value is roughly 0.26. And we're going to see next in the calculation that the probability of failure in this scenario is not at all 0.26. If we want to do this correctly, we need to represent this in a bivariate domain because we have two random variables. So a first axis R is the resistance in blue. So we have our marginal PDF here. The second axis S represents in green here this marginal PDF. And then we need to define our boundary. That represents the case where the resistance equals the solicitation. So both axes here are the same. Here we just see this graph kind of from the top. So this is the limit that defines my failure and my survival domain. So whatever is in that pink zone on either graph is going to be my failure domain. Why? Because at any point here above the diagonal, the solicitation is greater than the resistance. Okay, so I'm bound to have a failure. And then if we want to compute the probability of failure, we need to look at the joint probability density. In that case, since both are independent, both random variable, I can obtain the joint PDF that represents this curve by simply multiplying for each grid point the marginal probability density to obtain the joint probability density. So in that case, I can draw the surface or either represent as a contour plot, okay, like a kind of topographical map of my joint density. And if I want to compute PF, my probability of failure, I need to integrate over the failure domain. So the failure domain is all the value for which the resistance is lesser or equal than solicitation, my pink domain here. I need to integrate for my joint PDF here for all possible R and S, such as I'm in my failure domain. And the result of the area under this part of my joint PDF is going to give me, if I could make the computation for this special case, 0.073. And we see that this is much lower than the 0.26 we saw by looking at the area between the intersection of the curve that we saw that was a wrongful representation in the previous slide. So, okay, we need to integrate, but we know that it's hard to integrate in two dimension. And what we're going to see later on in the course, we're going to integrate in many more than two dimension. We don't want to do this. So the first thing we're going to see is how can we bypass the problem and reduce our integration from a two-dimensional one to a one-dimensional integration. It would be easier to do. So to do this, this is a first introduction case. We're going to say that we want to model that joint probability density between the resistance and solicitation by a conditional and marginal, because we saw in the module 0, when we reviewed the concept of probability theory, that a joint probability density could always be modeled by a conditional times its marginal. So R given S times the probability density for S. So in that case, if I use this artifact, I can model my probability of failure as that joint integral for that conditional times that marginal. So I first integrate with respect to the resistance from 0 to S, and then I integrate with respect to solicitation. So what does it correspond to? It's like, since I start integrating with respect to R, it's like if I cut my failure domain in horizontal slices. Okay, and I always integrate from the lower bound, in this case 0, up to my solicitation. And I keep integrating like this, and I then sum for all my slices vertically with respect to the solicitation. And there's something interesting here. We can see that the solicitation is independent from the resistance. So I can push that PDF or solicitation inside my integral. And what I find is f of r given the integral with respect to R of my conditional PDF is actually my CDF evaluated at my solicitation S. So I can simplify this in a one-dimensional integral where the inside integral is directly a CDF that I can directly evaluate. And this represents the probability that the resistance is less than the solicitation given a solicitation value that is going to be then weighted by the probability density of having that specific solicitation. Okay, that might be tricky. We're going to come back to another visualization in the following slide. But as we saw earlier in our revision module, we can model a joint probability density by a conditional times a marginal, but there are two ways to do. So either it's R given S or it's S given R times the marginal probability density of the resistance. Okay, so now we're going to flip the problem. We're going to still integrate, but with respect to this decomposition, so that we're going to have now vertical slices. I'm going to first integrate from R up to infinity. So from the resistance, because this is the boundary of my domain, and I'm going to make vertical slices like this, and I'm going to integrate with respect to all the resistance slides. So what is the height of all of these? Now I can do the same thing. I can push, because the resistance is independent of solicitation. I can bring this out of the first integral. And here, instead of having the CDF, I'm going to have the complement of the CDF, because the CDF would give me the slices underneath, whereas what I want is the slices above from a given value up to infinity. So I need to take the complement of the CDF, and then I can do the same trick in reducing a 2D integral in a 1D integral involving a cumulative density function. Okay, so let's look again a little more detail in the case where the resistance is independent from the solicitation. So in that case, my conditional PDF of R given S is going to be f of R, and S given R is going to be f of S. So in that case, I can represent my probability of failure as this one-dimensional integral from 0 to infinity, because this is the domain of my log normal, of my CDF f of R evaluated at S times my probability density function for S. And I integrate this with respect to all S values. And again, keep in mind, this represents the probability that my resistance is lesser or equal than the value of solicitation. So if we want to represent this graphically, we see this is the probability density function for my solicitation, probability density function for my resistance. And what does this equation boils down to is we have here the CDF evaluated at a given S value. So if I have my S value around, say, 12 kilonewton, the probability that the resistance is less than 12 kilonewton is going to be given by this area under the curve. And this area under the curve is actually the CDF of my resistance evaluated at that 12 kilonewton value. It represents that area in pink here. And I need to weight down that specific value of probability of failure for 12 kilonewton of solicitation by the probability density that this solicitation is going to occur. And this is what we do here, and we integrate over all possible values of solicitation. When I represent my conditional probability and my marginal the other way around by the resistance given the solicitation, I'm simply flipping the problem over. So I'm going to say, I'm going to look at what is the probability that solicitation is lesser or equal than resistance. That represents the blue area under the curve, and I take 1 minus because the CDF would give me the other half underneath the green curve. Now I want to flip that over, so I take 1 minus to get the complement, and I need to weight that area under the curve, probability that solicitation is lesser or equal than resistance, by the probability density of having a given resistance value. So in that case here, and I integrate over all possible resistance as outlined by the blue curve here. So this is if we would want to represent the reliability problem on a single axis and we want to do it accurately, this is how we would need to depict it. We cannot look at just simply the intersection between the two curves. This doesn't represent my probability of failure. It's really this way if we want to represent on the same axis those two quantities. This is the proper way of doing it. So now let's see a key concept that's going to help us define our beta or reliability index. And that key concept is named the safety margin. So we're going to model a safety margin, Z. So whenever you're going to see Z in this class, we're going to refer to a safety margin. And safety margin is going to be the distance between my resistance and my solicitation. So Z equal R minus X. So we're going to send C in this problem that as long as the resistance is greater than solicitation, we're going to be in our survival domain. The opposite, if the resistance is less than solicitation, we're going to be in our failure domain. So in that case, the event where z is lesser or equal to 0 will be our failure domain. So we can compute our probability of failure as the probability that z is lesser or equal to 0, and that corresponds to evaluating its CDF of z for the value of 0, because this is going to correspond to the integral from minus infinity up to 0. So in that case, if we have the probability density function for z here, so it has a given mu z and standard deviation sigma z, my probability of failure is going to be equal to the integral from minus infinity up to 0. So this denote here PF. So in this case, since z is a linear function of R and S, I can directly use the equations that we saw in the revision module 0, where we can look that for the mean of z is going to be simply the mean of R and S, assuming that R and S are themselves Gaussian. So we're going to have mu z equals mu R minus mu S. And the variance for z is going to be the sum of the respective variance for each random variable minus 2 times the correlation coefficient between R and S times their respective standard deviation. And here z, if R and S are themselves Gaussian, z is also going to be Gaussian. And we now have the mean and variance for defining this random variable. And we saw as well that in module 1 that we can go from an original Gaussian space to the standard normal space, which has a mean 0 and standard deviation 1. And we can make this kind of transition between the original state and the standard normal state by taking my random variable z, subtracting its mean, and dividing by its standard deviation. And so if we do that transfer from the original to the standard normal space, we want to evaluate in that standard normal space for z equals 0. Okay, so for z equals 0, it will correspond in my u space, which is a standard normal 1, at minus mu z over sigma z. So in that case, if we look now at the PDF for my standard normal space, mean 0 and standard deviation 1, now my failure domain is defined at a quantity that is minus mu z divided by sigma z away from my origin. And this is what's going to define here my reliability index beta. This is what you're going to typically see in basic description of what is reliability, structural reliability. This is going to be the definition of that reliability index. And how is it obtained? Exactly with the development we just did here using our safety margin. So what it tells us that reliability index, it tells me that in the standard normal space, so a Gaussian random variable with mean 0 and unit standard deviation, my failure domain is a distance minus beta away from the origin. Okay, so I can directly evaluate here my probability of failure as being this area under the curve. And since I know that I'm in a standard normal space, I can directly go from beta to PF by evaluating my standard normal CDF. So a CDF or Gaussian random variable would mean 0, standard deviation 1, at the value minus beta. And that's going to give me directly my probability of failure, where in this case, f of u is capital phi, the standard notation for standard normal CDF. So if we recap, we have a safety margin, which is equal to the resistance minus solicitation. My event that defines the failure is all the values z that are lesser or equal to 0. This is what's going to define my probability of failure, the probability that this event happened. Then we want to go in the standard normal space because we don't want to evaluate our CDF for z equals 0. We want instead to go in the standard normal space where the probability of failure is going to be the probability that the standard normal random variable u is lesser or equal than minus mu z over sigma z. Okay, we saw that because u is a standard normal random variable. Gaussian would mean 0, standard deviation 1. This is the standard notation for the standard normal Gaussian PDF. And we can go from z to u by taking z, subtracting the mean, dividing by the standard deviation. So we're going to go in that standard normal space where beta, which is mu z divided by sigma z, is my reliability index. And in that case, we can see that if R and S are defined as multivariate Gaussian, these methods of computing the reliability index or the probability of failure are actually exact. There's no approximation entailed in using this methodology. We're going to come back to this with an example in a few slides. So before this, let's just look at what is the relationship between beta, my reliability index, and my probability of failure on the vertical axis. So, and we can see here, if we look, the typical reliability index for structures are going to be around 3.5, which gives us a probability of failure of about 10 to the minus 4. If we look at a reliability index of 2, we're in the surrounding of 10 to the minus 2, 0.01 is probability of failure. This is fairly high. The opposite, if we're at 10 to the minus 6, 1 in a million, we're roughly at 4.5 in terms of reliability index. So you can see for a unit change in beta plus and minus 1 unit, we can span several order of magnitude in terms of probability of failure. Okay, so small difference in beta makes a big difference in change of probability of failure. So now let's review our initial example where both R and S are are log normal random variable. So we have the same mean we defined as before, the same standard deviation, both are statistically independent. So now if we compute mu z and sigma z, so we're going to obtain roughly 10 and 7. So in that case, if we assume the simplification that z equal r minus s, which is going to be roughly a Gaussian. So we're making simplification because we cannot directly subtract log normal, but we're making simplification just for the sake of this example here. So in that case, that would be that mu z plus and minus sigma z, and pf is here the area under the curve. So we saw that beta is mu z divided by sigma z. So in our case, we compute 10 and 7, we divide the two, we're going to get 1.41. That would be our beta. So it means that our probability of failure is 1.41 units away from my origin. So that defined here what would be my failure region. So if I want to evaluate numerically what is PF, is going to be my normal CDF of minus 1.41, which would give me here 0.079. And here I numerically exactly compute what should be the real probability, 0.073 versus 0.079. I'm not exactly on it, but I'm not too far away. And why I'm not exactly on it, in this case, is because that would only be exact if my R and S would be normal random variable. So since here I'm using log normal, I'm not exactly matching the theoretical result. Okay, let's go one more step. So now we're gonna go away from a safety margin and we're gonna go with a safety factor. So with a safety factor, we're gonna look at the ratio between R and S instead of looking at the distance between R and S. So now I'm gonna say Z is R divided by S. So in this case, I can say that it is equivalent in kind of discriminating between the resistance and the solicitation, because I can say that when R is greater than S, I'm going to have something that is above 1, and S is greater than solicitation, I'm going to get something below 1. Okay, where Z is equal to ln of R minus ln of S. So basically, by looking at the ratio, if I have log normal random variable for R and S, I can directly divide log normal random variable and still have a log normal as the result for S. So keep in mind as well that the cases where R is lesser or equal to S is equivalent to the log of R being less or equal to the log of S. So both define exactly the same limited function that separate the failure and the survival domain. And in this case, like log of R and log of S are following log normal distribution, I can directly use what we saw in module 1 for the review of probability density function to compute the mean of Z exactly. Okay, because when I'm dividing log normal random variable, I can directly subtract their expected value taken in the log space. That would give 0.77 for the mean of Z. And for the variance of Z is going to be the sum of the variance in the log transform space minus 2 times the correlation coefficient, in this case 0, times the respective standard deviation taken in the log space. That would give me a standard deviation of 0.53. So we said earlier that the exact value for the probability of failure was 0.073. In this case, if I take the ratio of the mean and the standard deviation, I evaluate the standard normal CDF for this, I'm going to get 0.073. So we can see that here we have an exact representation if we take a safety factor to represent the failure domain of my probability of failure. So we saw in module 1 when we review probability density function, what is going to be influencing our choice of having a normal PDF or log normal, a gamble, a beta, a Rayleigh distribution to model or distribution. What influence this choice? So we're going to look at this through an example. So let's assume that we have the mean for the solicitation that is 10. We're going to have the coefficient of variation for resistance solicitation that is 0.3. And we're going to have the resistance that is independent for the solicitation. And what we're going to look at is a graph of our, on the vertical axis on the left here, what is our beta or reliability index as a function of the ratio between mu s that is fixed 10 and mu r. So if mu r equal mu s, so the ratio is equal to 1, we can see that whether I choose a normal or a log normal, I'm going to have the same value of beta. And keep in mind here, a beta equals 0 correspond to a probability of failure of, in this case, 0.5. Okay, so the left graph is beta, the right axis is PF. So as I'm going to increase the ratio between mu r and mu s, you can see that choosing a log normal distribution is going to diverge. Okay, the more this discrepancy is, the more the I change the ratio. So the more mu r is greater than mu s, the more my two choices are going to diverge in terms of beta or probability of failure. So what caused this effect? That a small change in the choice of probability density function will give me a large change in the value of beta or in the value of probability of failure. So I can go from 0.01 to 0.001. So if we look at this problem in a multivariate space, okay? So I'm going to assume right now that the ratio between mu r and mu s is 1. So both have the same value. So we can see that both probability density function simply overlap. So if we would look in a multivariate domain, it would look somehow like this. So my joint PDF is just centered on the boundary between my failure and my survival domain, such as the current probability of failure is 0.5. 50% of the PDF is on the failure domain, 50% is in the survival domain. If I start to shift away by a factor 2 mu r over mu s, we can see that now I'm shifting my joint probability towards the survival domain. So now we see that PF drop. If I do this a little more, so a ratio of 3, it dropped even more. If I keep doing this with a factor of 4, it dropped by a lot. And what we can see, and typically we're going to be in the order of 5 to the e to the minus 4 in terms of probability of failure. And in such a case, we can see that the failure domain, it's really only happening in the tail of the distribution. And the tail of distribution is very poorly described by the position measures, such as the mean, and the dispersion measures, such as sigma. Okay, so it's not because two probability density looks very similar in the center of the distribution that they look the same in the tail. And whenever we'll want to compute the probability of failure, we'll want to compute what happened in the tail of this distribution for rare events. So even if all those distribution, the normal, the gumball, the beta, the log normal, all look the same at the center of the distribution, they look very drastically different in the tail. So if we zoom in, we see the discrepancy with the normal being the one that has the least probability content in the tail. If we go even farther out in the tail, the normal is fully flat. And this is what matters, okay? And so that's why you need to refer to probabilistic code in order to define for a given phenomena you want to model, which probability density function should you be using with what parameters, okay? Because if you don't make an appropriate choice, you might underestimate or overestimate the probability content in the tail, and that's going to have a drastic impact on the probability of failure you will be estimating. So now we're going to see the last subsection of this module where we're going to define what is a limit state function. And this is what the remainder of the course is going to build upon. And this is the key concept to be used in structural reliability. So we're going to define this in detail. We're going to look at an example, and we're going to see an overview of system reliability problems that are going to be covered in detail in module 9. So first, let's look at the limit state function, what it is. So let's assume we have a set of n random variables, okay, that are directly observable. These could model, say, the ultimate resistance of concrete, or it could be Young's modulus of something, or it could be a variable associated with defining the solicitation associated with the loading applied on our structure. And so we're going to define R of X, S of X, A of X. Okay, so R of X could be the resistance that itself, it'll involve some or all of these n random variable. The solicitation is not going to be modeled explicitly either as one random variable, but more as a function that involve these random variables. Okay, where the resistance and solicitation are not directly observable, only X is. So for instance, if we want to make a simple case, we're going to define g of x as a limit state function. So it's a function that says that involve x, my random variables, so that, for instance, I'm going to have my resistance that involve x minus my solicitation that involve x. Okay, where r and x are not going to be random variables themselves. They're going to be function of random variables. And we're going to say that the event where g of x equals 0 is going to be my limit state surface. Okay, so we have my limit state function. My limit state surface is going to be the boundary between the failure domain and the survival domain. And omega is going to be the event, such as we have my failure domain. So all the possible value x such that g of x is lesser or equal to 0, all the case corresponding to the failure. And my probability of failure, PF, is going to be computed as a probability that my limit state function g of x is less of x than 0. So that represents, in the multivariate case, my n-dimensional x vector, the integral over omega, so all my coordinate x that are in the failure domain. So it's going to be that multivariate integral over my joint probability density for x, for all x's. Okay, so let's look at an example. How can we now formulate a reliability problem, not as having R and S as explicit random variable, but having variable involved in the definition of either R or S, or both, as random variable. So in this case, we're going to have D, which is the dimension of my bar. So in this case, we have D, the dimension of my bar. So I can assume that the dimension here as a mean of 10 millimeters, the standard deviation of 2. This is the dimension itself of the bar. So the area is going to be D squared. And the force applied is going to be D squared times the limit f of y. So the ultimate, the yield strength of my material. In this case, assume it's steel, is going to be 300 megapascal. The solicitation here for solid-gas publicity is going to be directly modeled by a random variable with mean 15 and standard deviation 5 kilonewton meters. And I'm going to assume that the solicitation is independent of the dimension from my bar. So in this case, x, my vector of random variable, is going to be d, the dimension, and s, the solicitation. And as we described earlier, the resistance could be modeled as d squared times f of y. The area of my bar times the yield strength, so 300 MPa. So my limit state function could be modeled as r, that is function of my dimension, minus the solicitation. So d squared f of y minus s. So in that case, it would look like a graph such as this one. Okay, so if we look at it in detail here, we can see we have the same thing. We have the solicitation on this axis. We have the dimension on this axis, and the vertical axis is the value returned by my limit state function. And what you can see here in purple, this is my limit state surface, okay? The boundary that define my failure domain from my survival domain. And if we look at it in 3D, you can see that this pink surface is the intersection between the plane that is giving equals g of x equals 0. This is the the what this pink line looks like. So anything above g of x equals 0 is surviving. Anything below is my failure domain. So if we represent that pink curve over my domain, it looks like this, where we have the intersection between my joined PDF and the limit state surface, or the same thing here on my joint PDF. So you see that the integral of my joint PDF in that region is going to give me my probability of failure. So if we do this, we want to integrate that joint PDF over my domain omega. That's going to, in this case, since we have two random variables, it's going to be a b-dimensional integral. So I'm going to first integral with respect to all s from what value? From the value of my resistance, of my solicitation. So in this case, my solicitation. So I know that my solicitation starts from my failure domain. So it means that this equals 0. If this equals 0, I can sense s on the other side. So s equal my resistance, which is equal to d squared f of y. So that's why my lower bound here is d squared f of y. It's the equivalent of, say, I'm going to integrate with respect to all values that are here. And this equation is d squared f of y, just by the relation g of x equals 0. So g of x equals 0 is d squared f of y minus s. So by sending s on the other side, the left-hand side of the equation, we get s equal d squared f of y. So I first integrate with respect to s from these bounds, and then the dimension from 0 to infinity. I would get as a result for an approximation of the probability of failure 0.08. And that represents, as we just say, the integral over this failure domain. So let's do a recap. We're going to see this graph over and over because this is what we're going to be working on for the remainder of the semester. We're going to have x, a set or a collection of n random variable. F of x is going to be the joint probability density. G of x is going to be my limit state function. And omega is going to be my failure domain. So my failure domain is everything in pink here. This is my limit state surface. So my frontier, my boundary between the failure and the survival domain. My limit state function d of x, we don't see it explicitly in this graph, but this is as we saw here. So something that is negative in the failure domain, positive in the survival. So it would go kind of into the screen in that region and above the screen or out of the screen in this white region. So let's look now at more kind of practical example of what the limit state function could look like for practical problem. So imagine we have a elastic buckling problem. So we can say that we're going to have our limit state function, which take into account parameters or random variables, such as the Young's modulus, the inertia of my column, k, my elongation factor, L, the length of the column, and P, the load applied. So the resistance for elastic buckling is modeled by P squared, the Young's modulus, times the inertia of my cross section divided by elongation factor K, and my length of my column, all of this square, minus P. Okay, so that would be an example of limit state function for elastic buckling. If we have an earthquake, we're typically going to define the demand during an earthquake as the residual displacement between two floors in case of multi-story buildings. So in that case, we can say that G of I that represent the survival or failure of a given floor as the inter-story drift that is modeled versus what is the capacity of my building. So for one story, I'm going to have just G1 of X, but I can have M floor in my building. So if I want to model my joint probability of survival, I need to define the limit state function for my whole building. So in that case, I'm going to take the minimum of my limit state function for my m floors. Because if any of the floors fail, I can assume that my building has failed under earthquake loads. Then if you kind of do 3D final modeling, you're going to say, I'm going to have a failure criteria. Let's say you use von Mises failure criteria. You're going to say that the yield strength is equal to this von Mises representation using principal components, or principal stress, sorry. So in that case, we can represent this as g of x equals 0 being my limit state. If I send on the other side my yield strength minus the von Mises stress computed using principal stress. Okay, these are typical example how you're going to formulate limit state function. Now, if we take an overview of different classes of problems for either component reliability or system reliability, we're going to say that if we have a single component, we want to formulate its limit state function. We're going to define g of x, a function that's going to be continuous and differentiable. Okay, so it would represent something like this. If we have x1, x2, we're going to have here the limit state surface and the limit state function that represent both the survival and the failure domain. If we have a system reliability problem where we have components that are assembled in a series problem, like remember in module 1, we said a case where we need to cross n bridges to go from point A to point B, or you can imagine a bridge that is made of multiple span. So if any of the span fails, the bridge will be deemed to have failed. So in that case, we can represent the limit state function as the minimum of all the individual limit state function. So basically, the failure domain represents the intersection of the limit state surfaces, or the intersection of the failure domain for any of my limit state functions. If I have a parallel system, so imagine a bridge span made of multiple beams, so we can say that we need all beams to fail in order to have a failure of my span. So in that case, I'm going to take the max of the limit state function for each of my individual beams. Okay, because if any of them survive, my bridge is still deemed to survive. So in that case, I'm going to look not at the union, but in this case, at the intersection of all the failure domain. And in the general case of a system reliability problem, we could have a mix of the components are in parallel and a mix of components are in series, okay? And we're gonna have a mix and match of what is the, at the end, failure domain. So what I'm gonna do is that I'm gonna typically regroup all the parts that are in parallel and then look at them as subcomponent or subsystems that are themselves in series. Okay, we're going to cover all of this in details in module 9. So what are the challenges associated with all these problems? First is that when we want to assemble multiple components, we need to see concepts such as couplings and that will allow us to model the either parallel component or series problem and assemble them in order to make general system reliability problem. We're going to cover this in detail in module 9. Then the second challenge we're going to tackle in the following module is that how can we integrate when the number of variable is more than 2? Because I can fairly easily integrate in 3 dimensions, but what happens if n equals 100? I don't want to do manually 100 dimensional integrals. I cannot do this. So first, it's not possible to draw the joint probability density, so it's not really possible to visualize what's going on. And it becomes increasingly difficult as the number of dimensions increase to make that integration. So the following module are going to see, we're going to see how to perform such integration using either analytical methods, using FOSM, FORM, and SORM. So first order, second moment, first order reliability method, and second order reliability method. But first, we're going to see how can we perform such integration using numerical approximation. So the next thing we're going to see is how can we do this with Monte Carlo integration. So in summary, if you see representation like this of this area being represented as the probability of failure, you can see that this is a misleading one. So in a special case where we're going to directly represent R and S as random variable, we're going to represent R as the resistance, as the solicitation, and the cases where R is less or equal than the solicitation represents my failure domain. So we can see in general, the probability of failure can be represented or describe the probability that my resistance is less or equal than my solicitation. So we use our safety margin in order to where Z equals the resistance minus the solicitation, or a special case of safety factor as R divided by S, in order to define our reliability index beta, which is, as you typically see in the manual, given by these quantities. Okay, and this equation is directly derived from that margin of safety formulation that we saw earlier. And at the end, my reliability index beta represents mu z divided by sigma z, where mu z is the numerator here, sigma z what we have on the denominator. And we could saw that we can compute directly PF from beta by saying that it's evaluating the standard normal CDF at a quantity minus beta away from the origin. So we can directly go with this formulation from beta to PF. And what we're going to see in the following module is that if we have access to beta, we can directly easily compute PF by using the standard normal CDF that is easily accessible. We saw that why does it matter to choose your correct probability density function to model your quantity of interest is because we're looking at what's going on far out in the tail, because in the context of structural reliability, we're looking at small probability of failure that are occurring far out in the tail here, where there can be very large discrepancies between the probability density function values out in the tail, even if the core content around the mean all look the same. So we're going to define in the general way limit state function that we're going to use to build structural reliability problem. So X is going to be our collection of basis random variable. We're going to have g of X, which is our function, limited function, g of X equals 0, or limit state surface, and omega, which is our failure domain. All the values of X such that I'm in my failure domain so that g of X is less or equal to 0. And we're going to always use representations such as this one. And we're going to define the probability of failure in a general way as the integral over my domain omega for my joint probability density function for f of X, my collection of random variables that are involved in the definition of either the resistance or the solicitation. So that will include our first module 2, where we define how can we formulate reliability problem. So before tackling module 4, where we're going to explicitly see how to approximate such probability of failure using numerical methods such as Monte Carlo, we still have to see how do we define this f of X? How do we define that joint probability function in the case where we have different marginal probability density function, and we can have some correlation structure between those. So module 3 is going to cover these aspects.